What's your name?
Kami.
Kami. David, right over there. What's your name? Matt. David. Juhei. David. Max. Nice to meet you. James. Nice to see you. Here, I'll get more chairs. What's your name? Peyton. David. And 2 more. Actually, can one of you come down to this end here? What's your name?
I'm Andrea.
Andrea. Nice to see you. And your name?
Hi,
Pico. David. Nice to see you. OK. Colton has a T-shirt for each of you. Very Harvard-esque here. And each of these shirts, as you're about to see, has a number on it. And that number is, I'll go ahead and put them on if you wouldn't mind. OK, thank you so much. So I dare say we've arranged our humans, much like the lockers, in an array. Like we have humans back to back to back to back. But this is actually both a blessing and a constraint because we only have 8 chairs. So there's really not much room here. So we're confined to just this space here. And I see we have a 4, 8, 5, 2, 3, 1, 6, 7. So this is great. Like they are unsorted by definition. It's pretty random. So that's great. So let's just start off by this. Sort yourselves from 1 to 8, please. OK. All right. Well, what algorithm was that? Look around, figure it out. OK. Well, human ingenuity. Very well done. So can we? What was like a thought going through any of your minds? Find the chair, or find the right chair. So go to the go-to location. Good. So like an index location, right? Arrays have indices, so to speak, 0, 1, 2, all the way up to 7. And even though our shirts are numbered from 1 to 8, you can think in terms of 0 to 7. So that was good. Anyone else? Other thoughts?
Yeah, I mean, this is something we implicitly think of, but no one told us that it was ordered right to left. Like we could have done it left to right.
OK, absolutely. Could have gone from right to left instead of left to right. But at least we all agreed on this convention too. So that was in your mind. OK, so good. So we got this sorted. Go ahead and re-randomize yourself if you could. And what algorithm was this? Just random awkwardness. OK, so that's fine. So it looks pretty random. That'll do. Let's see if we can now reduce the process of sorting to something a little more algorithmic so that, 1, we can be sure we're correct and not just kind of get lucky that everyone kind of figured it out and no one was left out. And 2, then start to think about how efficient it is, right? Because if we've been gaining so much efficiency for the phone book, for our context, for Eric coming up, like we really should have been asking the whole time, sure, you save time with binary search and divide and conquer, but how much did it cost you to get to a point where you can use binary search and divide and conquer? Because sorting, if it's super, super, super expensive and time consuming, maybe it's a net negative, and you might as well just search the whole list rather than ever sort anything. All right, so let's see here. 6 and 5. I don't like this. Why? 6 supposed to come after 5. And so can we fix this, please? All right, and then let's see. OK, 6 and 1. Don't really like this. Can we fix this? Very nice. 6 and 3. OK, you really got the short end of the stick here. So 6 and 3. Could we fix this? And 6. Yeah. OK. OK. 6 and 7. Good. All right. So that's pretty good. 7 and 8. Nice. 8 and 4. Sorry. Could we switch here? All right. And then 8 and 2. OK. Could we switch here? OK. And let me ask a somewhat rhetorical question. OK. Am I done? OK, no, obviously not. But I did fix some problems, right? I fixed some transpositions, numbers being out of order. And in fact, what's your name again?
Kami.
Kami kind of bubbled to the right here, if you will. Like you were kind of farther down, and now you're over here. And like the smaller numbers kind of, 1, like, my God, like he kind of bubbled his way this way. So like things are percolating in some sense, and that's a good thing. And so, let me try to fix some remaining problems. So 1 and 5, good. Oh, 3 and 5, could you switch? 5 and 6. OK, 6 and 7. 7 and 4, could you switch? OK. And 7 and 2, could you switch? And now I don't have to speak with Kami again because we know you're in the right place. So I actually don't have to do quite as much work this time, which is kind of nice. But am I done? Like, no, obviously not. But what's the pattern now? Like, what's the fundamental primitive? If I just compare pairwise humans and numbers, I can slightly improve the situation each time by just swapping them. And each time, now, I'm sorry, Pico is in number 7's place. I don't have to talk to him anymore because he's now bubbled his way all the way up to the top. So even though I'm doing the same thing again and again, and looping again and again isn't always the best thing, so long as you're looping fewer and fewer times, I will eventually stop, it would seem, because 6 is going to eventually go in the right place, and then 5, and then 4, and so forth. So if we can just finish this algorithm, good, 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 not good. OK, 6 and 2, not good. If you could swap. OK, what's your name again?
Peyton.
Peyton. Peyton is now in the right place. I have even less work now ahead of me. So if I can just continue this process, 1 and 3, 3 and 5, 4 and 5. OK, and then 2 and 5. And then what's your name again?
Matt.
Matt is now in the right place. Even less work. We're almost there. 1 and 3, 3 and 4, 4 and 2, if you could swap. OK, almost done. And 1 and 3, 3 and 2, if you could swap. Nice. So this is interesting. It would seem that, in the first place, I kind of compared 7 pairs of people. And then the next time I went through, I compared how many pairs of people maximally. Just 6, right? Because we were able to leave Kami out, and then we were able to leave Pico out, and then Peyton. And so the number of comparisons I was doing was getting fewer and fewer. So that feels pretty good. But you know what? Before we even analyze that, can you just randomize yourselves again? Any human algorithm is fine. Let's try one other approach, because this feels kind of non-obvious, right? I was fixing things, but I had to keep fixing things again and again. Let me try to take a bigger bite out of the problem this time by just selecting the smallest person. OK, so your name again is? Juhei, number 2. That's a pretty small number, so I'm going to remember that in sort of a mental variable. 4, no, you're too big, too big, too big, too big. Oh, what was your name again? James. James is a 1. That's pretty nice. Let me keep checking. OK, James in my mental variable is the smallest number. I know I want him at the beginning, so if you wouldn't mind coming with me. And I'm sorry, we don't have room for you anymore. If you could just, oh, you know what? Could you all just shuffle down? Well, I don't know if I like that. That's a lot of work, right? Moving all these values. Let's not do that. Let's not do that. Number 2, could you mind just going where James was? OK. So I've kind of made the problem a little worse, and that now number 2 is farther away from the goal. But I could have gotten lucky, and maybe she was number 7 or 8. And so let me just claim that on average, just evicting the person is going to kind of be a wash and average out. But now James is in the right place. Done. Now I have a problem that's of size 7. So let me select the next smallest person. 4 is the next smallest, not 8, not 5, not 7. Ooh, 2. Not 3, 6. OK, so you're back in the game. All right, come on back. And can we evict number 4? And on this algorithm, if you will, I just iteratively select the smallest person. I'm not comparing everyone in quite the same way and swapping them pairwise. I'm doing kind of more macroscopic swaps. So now I'm going to look for the next smallest, which is 3, if you wouldn't mind popping it on here. Kami, we have to unfortunately evict you, but that works out to our favor. Let me look for the next smallest, which is 4. OK, you're back in. Come on down. Swap with 5. OK, now I'm looking for 5. Hey, 5, there you are. OK, so go here. OK, looking for 6. Oh, 6, a little bit of a shuffle. OK, and now looking for 7. Oh, 7, if you could go here. But notice I'm not going back. And this is what's important. Like my steps are getting shorter and shorter. My remaining steps are getting shorter and shorter. And now we've actually sorted all of these humans. So 2 fundamentally different ways, but they're both comparative in nature because I'm comparing these characters again and again and again and swapping them if they're out of order. Or I'm at a big higher level going through and swapping them again and again and again. But how many steps am I taking each time? Even though I was doing fewer and fewer and I wasn't doubling back, the first time I was doing like n-1 comparisons. And then I went back here. And in the first algorithm, I kind of stopped going as far. In the second algorithm, I just didn't go back as far. So it was just kind of a different way of thinking of the problem. But then I did, like 7 comparisons, then 6, then 5, then 4, then 3, then 2, then 1. It's getting smaller. But how many comparisons is that total? If I've got like n people, n being a number, it's not as bad as factorial. We'd be here all day long. But it is big. It is big. Let's a round of applause if we could for our volunteers. You can keep the shirts if you'd like as souvenir. Thank you very much.